All right, good evening and welcome to lecture number 16 for MT225. Uh, Tonight we'll be moving into a slightly new topic. We'll be taking a look at truss analysis with method of sections. And usually the way it works out, method of joints and method of sections, those are our two big methods of analyzing trusses. Some people like method of joints a lot. Some people like method of sections a lot. Both can be used to get you to the right answers in the end. And in fact, in some problems, you have to kind of mix and match. You do a little of one method, maybe a little of another. We'll take a look at some problems like that later on this week. Um, so there are some issues here and there with it, specifically when it comes down to tension versus compression that we have to keep straight. But once you get a hang of that, it's pretty straightforward method to use. So let's get started here. Homework 6 has been posted, was posted last week. It is due on Wednesday, and I'll open up the floor for questions here on that in a moment. And then we do have our next quiz coming up on Monday. Quiz number 5 will be based on homework number 6. So sometime over the weekend, I'll grade homework 6 and get that back to you. Post the solutions online, and then the exam or the quiz will be due on Monday, and that'll be based in method of joints. About the only time when you're required to use one method or another is when the problem says to use that method. So, for example, the problem we'll likely have for Monday's quiz will say use method of joints to determine the stresses and tension and compression in the members. So sometimes the problems tie your hands, sometimes they leave it wide open. So let's see, homework questions. There's been a question raised about homework problem number 1. So let's go and take a look at that. Um, as is my tradition on Monday nights, I'll just kind of give you some hints towards setting the problem up, but I won't work it out for you. On Wednesday night, if there's one of the, what do we have here, 4 problems, 3 problems that you want to see worked out in full detail, let me know and we'll work it out. So the question was with problem 1. Usually the question on that one is that it doesn't seem to have enough information to be able to solve because I don't have any geometry on there. We would say this problem has no scale. It has no sense of size to it. It could be a few inches wide. It could be a few miles wide. You can't tell from the drawing. But we can say some things about this. We know our first step with method of sections or method of joints is to solve the external problem. So we have to find reaction forces at A and at C, the pin and the roller support. Well, the only tool we have at this point to be able to do that, since we don't have any geometry, is to use symmetry. And it's safe to make that assumption. In fact, that's why I say symmetry may be useful in finding the reactions at A and C, is a little bit of a hint there. Uh, because you have no scale, you have basically 2 choices. You can either say, I don't have enough information, I can't solve the problem, which is not a great way to approach an engineering problem, or you can make assumptions that help you to solve the problem, but don't trivialize the problem. That's kind of the guideline with respect to assumptions. When you make assumptions in problems, they should be reasonable assumptions, but not assumptions that either make the problem so easy that that the solution becomes just a 30-second, okay, obviously this is the answer, or that really wouldn't change the problem setup at all. So you want to make judicious assumptions, and that's a lot of what being an engineer is about. When making these kinds of designs, you have to sometimes make assumptions, and they have to be reasonable and even in some cases defensible assumptions that you're willing to defend. Now here, symmetry is not uh, a bad option because we can either use symmetry or not be able to solve the problem. And not solving the problem is never the right option. not in a homework assignment anyway. So if we've got symmetry here, we can say something about how this 10 kip load, which is right at the middle, is distributed. You can make a pretty logical argument to say, well, how hard should A be pushing up and how hard should C be pushing up if we've got 10 kips? So it wouldn't be too hard to come up with some assumption there. And since there are no side loads, there's not going to be an X direction reaction at A. So we've got symmetry to work with. So that gives you enough information now that you can solve at joint A and joint C. And in fact, you might even argue, well, I really only have to solve one of them. If you solve joint A, you'll get member AB and member AC. You don't really have to go and solve it at C because symmetry says the two sides are going to have to be the same. So whatever load member AB is carrying, member BC is going to carry that also. So symmetry is kind of the key to working out that problem. Any other homework questions before we proceed? All right then, so let's go over to the notes and take a look at the method of sections. So just as we're getting used to the method of joints, we get to change things and do a different method, a method of sections. So we're still doing truss analysis. The goal is still to learn everything there is to know about the truss, or at least everything we need to know about the truss. In some cases, we don't need to have every single member. Some cases we do, but in others we don't. And method of sections really shines when all we need are a subset of the members. We don't need every single member. So this works really well on trusses with lots and lots of members, where we only want maybe 3 or 4 of the critical members, maybe the ones that we think are most heavily loaded. And so this can really make it a lot easier to solve a truss without having to do a lot of work that ultimately doesn't give you useful answers. Method of joints would require that we work our way one way across the truss or the other way across the truss from one of the supports inward. Method of sections lets us jump right into the middle of the truss. And so that's pretty useful. So we'll see how that works. So method of sections. The first step is exactly the same as with method of joints. We find the external forces. We find the reactions at the supports. So we calculate our reactions at the supports. Nothing really changes there. So as long as you're feeling pretty skilled at solving your external problem, you already have a step up on method of sections. Here's where the difference is with step 2. Is we define what we call a section of the truss. Essentially what we're doing is we're using a system boundary. In the external problem, we had the system boundary wrap around the entire truss. In method of sections, we make the system boundary cut partially through the truss. And we set it up so that it cuts through no more than 3 unknown members. That 3 is kind of a special number. It happens to be the number of unknowns we can solve for in a non-concurrent force system. And that's exactly what we're setting up here. We're going to be setting up a non-concurrent force system. Effectively, what we do when we draw that system boundary is we're defining the system we're interested in and looking at the forces that the rest of the universe exerts on that something, whatever crosses or touches that boundary. Well, in the method of sections, what we're looking at is what forces are exerted on this section of the truss by the rest of the truss and potentially by the supports. So it's important the cutting surface cut through, or the system boundary cut through no more than 3 unknowns. If you cut through more than 3 unknown members, you're going to end up with more unknowns than equations, and that makes things kind of hard to work out. So with our section of the truss isolated, what we've really got is a non-concurrent force problem. And in a non-concurrent force problem, we had 3 equations of equilibrium. The sum of forces in the x direction equals 0. The sum of forces in the y direction equals 0. And the sum of moments about a point equals 0. So we can apply those 3 equations to the isolated section of the truss, and that will and in solving that, we will end up with our unknown stresses or our unknown forces. So we solve for our unknown forces. So let me skip to an example and kind of set things up before we go into a full solution. Um, if we needed every single member of the truss, if we needed to have the load on every single member, we would, after we finish our first section, we would go through and draw another section. We'd cut through 3 more members that we didn't know. And then we'd cut through 3 more, and we keep on doing that until we had everything. In the end, if you need to know everything about the truss, method of joints and method of sections involve the same number of operations. In method of joints, we have a long series of small, simple sets of equations, 2 equations, 2 unknowns. In method of sections, we have 3 equations in 3 unknowns. So we're taking bigger steps, more complex equations, but we're getting more information out of each step. In most method of sections problems, we only need a few of the truss members, so we don't have to do nearly as much calculation as we would in a corresponding method of joints problem. So we're going to skip over the tension or compression thing for a second here, and let's look at an example. Let's set up an example. So here I've got this truss. Now this truss has a lot of members to it. It has, let's see here, we've got 1, 2, 3, 4, 5, 6, 7, in between the top and the bottom, then 8 and 9 on the top, 10, 11, 12, 13. So 13 members total. That's a lot to try to work out. If we were going to work that out by method of joints, we would have to find our supports at A and E, and then we'd solve at joint A, and that would give us member AB and AH. We'd try jumping over to B, but we've got too many unknowns there, so we'd have to go to H, and we'd get GH and BH. Then we could go back to B, and we could kind of walk our way across the whole truss. But in this problem, what we're really interested in are just 3 of the members. We want to know what's going on here with members GH, BG, and BC. Well, those are only 3 out of the 13 members, and that's okay. We can do that. That's how the problem is set up. So let me copy this over here and work out our first step, get our reaction forces at the supports, good review for doing method of joints as well, and then we'll go ahead and draw our section. So here on this truss, we've got, looks like 4 bays. So each bay is 12 feet wide. So we've got a 48-foot section. And it's looking pretty almost symmetric. That load at C would put about 2,000 pounds on A and E, but we've got a little bit of asymmetry here at the top with our load here at H and F. So that's going to cause some differences in the support forces that we measure. But let's go ahead and sketch this over here, and we will go over to the board, so, or to the sheet. So let's see here. We got A, B, C, D, E, F, G, and H. 1,600 pounds at H. 2,400 pounds at F. And then we've got 4,000 pounds hanging from C. And let's see, this whole thing's 9 feet tall. And we have these 4 bays at 12 feet each. All right, so let's see what that looks like here. So there we go. We've got our truss set up there. Now, the first thing to do is find our external forces, solve the external problem. So even though this is a more complex truss than ones we've worked with before, the process is still the same. And in fact, we don't have to care at all about the internal structure of the truss to find the reactions. Essentially, our system boundary looks something like this. So our system is the truss itself, and everything that pushes on or gets cut through by that system boundary is an external force. So here we've got some external forces. We've got the 1,600 pounds at H, we've got the 2,400 pounds at F, we've got the 4,000 pounds at C, and then we've got our reactions at A and E at the pin and the roller support. So if we draw the free body diagram, it's going to look pretty similar to what we've already got here, except I'm not going to draw any of the internal detail. I've got a pinned support at A, so I'll have RAX and RAY. I've got this 4,000 pounds right at the center. I've got at E, REY. Then I've got these two forces up here at the top, the 1,600 pound and 2,400 pound forces. So there's our free body diagram. We'll copy the geometry as we need it. And we've got all of our forces here. We've got our reaction forces at A and E, and then we've got our 3 applied forces. So let's do the equations of equilibrium. Sum of forces in the x direction. All we've got is REX, or AX, excuse me. And RAX, since there are no other side loads in there, RAX must be 0. So no RAX. If we take our sum of forces in the y direction, we have, going just left to right, we've got a positive RAY, since x to the right and y up are positive, and counterclockwise moments are positive. We've got a positive RAY. We're down 4,000 pounds there. Got a positive REY. We're down 1,600 pounds, and we're down another 2,400. We can't do a whole lot with that just yet, but we can set it equal to 0. We'll come back to that one since we have 2 unknowns. As is usually the case in these problems, the moment equation is our saving grace here. We have our key to unlocking the problem, solving the moment equation. We have to pick a pivot point, and I'll pick joint A for that. Well, if we look at the forces that are going to have moments about joint A, RAY is not, so cross there. RAY will not have a moment since it pushes up against the joint. Its line of action goes through the joint, but every other force will. Every other force has some arm to it, some distance the line of action is from the pivot point. So let's go through and work them out. Here we've got 1,600 pounds at a distance of, looks like 12 feet. The line of action of that 1,600 pound force runs right down through B. B is 16 feet, there's 12 feet, excuse me, from A. So we have 16,000 times 12. And that would be a clockwise moment, since if we pin at A and push down there, we get a clockwise rotation. So that'll be negative. We've got this 4,000 pounds at C. C is 24 feet from A. So we've got 4,000 pounds at 24 feet. Pinned at A, pulling down at C, that's going to be a clockwise moment. So that's also negative. We've got 2,400 pounds. That's pushing down here with a line of action that goes through D. D is 36 feet from A. So that's our arm there. We've got 2,400 pounds times 36. Pinned at A, pushing down clockwise moment. So that's also negative. And then we have RUI. RUI is 48 feet away, so it's 48 REUI. Pinned at A, pushing up at E, that's a counterclockwise moment, and counterclockwise moments are positive. So moment equation with some fairly large numbers here. Suppose we could have shifted everything into kips to make the numbers a little smaller, but we can deal with pounds. So let's see here. If we crunch these down a little bit, we have negative 19,200 minus 4,000 times 24. That's 96,000. 2,400 times 36. That's minus 86,400 plus my 48 RUI, and that equals 0. So combining the numbers together, we get negative 201,600 plus 48 RUI equals 0. And solving that equation, we'd add 201,600 to both sides, divide by 48, and we get that RUI is 4,200 pounds. Kind of makes sense. We've got 4,000 pounds sitting right here in the middle, so that's an automatic 2,000 pounds on each side. But then we've got this extra 2,400 pounds pushing down here. And we've got this 1,600 pounds. Now, while A is going to support the majority of that 1,600 pounds, some of that's going to be over here on E. And while the majority of that 2,400 pounds is pushing down on E, some of it's going to be on A. So it's not too unreasonable to get up into the 4,200 pound range on that one. So now that we know that, we can go into our y direction equation and replace REY with 4,200 and figure out what RAY is. So RAY minus 4,000 plus 4,200 minus 1,600 and minus 2,400. That gives us 3,800. So RAY, without belaboring the algebra too much, is 3,800 pounds. And if you look at the total amount of force we've got pushing down here, we've got 8,000 pounds pushing down. So if we've got 4,200 pounds on one support, we got to have 3,800 on the other side to get that total 8,000. So now we know RAY has a force of 3,800 pounds and REY is 4,200. RAX is 0. So that's step one. We've got the reactions at the supports. Now here's how method of sections works. Let me redraw the free body diagram. It's always a good idea to redraw the free body diagram with the correct forces in and with all the details so that you have some place to start that has all the information. Then we'll reduce the amount of information that's there. So let me copy over the free body diagram here. So there's the truss, and this time we'll put the whole structure of the truss in there. So we've got A, B, C, D, E, F, G, and H. We know that there's a force pushing up at A, 3,800 pounds of force. We've got a force pushing up at E, 4,200 pounds. Then we've got our applied forces, our 4,000 pounds at C, 1,600 pounds at H, and 2,400 pounds at F. So that's what it looks like after we found our supports. Now, the problem that they're asking us about is not to solve the truss. It's not to find every single force. That would be just a tedious exercise. It wouldn't really be something that we'd work out on paper. It would be something we'd build a computer program to do, because doing method of joints across this whole truss is going to take a long, long time. Method of sections is at its best when we only want some of the members. And in this case, we want members GH, BG, and BC. Just those three. Well, to figure out what to do next, it's a good idea to go and tag those members. So member GH is right there, member BG is right there, and member BC is right there. Now those all line up, which means I could cut through them and only cut through those three members, not be forced to go and cut through another. Like, for example, if I wanted CD in here, if I tried to cut through there, I would be cutting through BG and GH. I'd also be cutting through CG to get to CD. But here I've got a nice straight shot through the three members that we're interested in. And that's how we determine our cutting plane, or our cutting surface. So the cutting surface is a tool. It's really a part of the system boundary. And I'm going to draw that in a slightly different color here to try to draw that out a little bit. So that's our cutting plane. Now the cutting plane, or the cutting surface, divides the inside from the outside, essentially. It's where we're trying to expose our unknown forces. It's really part of the system boundary, and system boundaries have to be closed. So as part of the problem, we have to decide, how are we going to close this? How are we going to close the loop? We can either close it to the left or we can close it to the right. Now, since there's a lot more going on here on the right, I've got three other forces to deal with. If I go to the right, the left is looking a little more attractive. So I'm going to complete my system boundary by closing it off to the left. Now here's where the magic happens. Remember that when we've got a system boundary, everything that goes on inside the system boundary, we really don't care about, as far as what kind of forces are there. Like, I don't care at all what member BH is doing, or what member AH is doing, or what member AB is doing. All that matters when we draw a system boundary is what touches the boundary, touches the edges, or what the boundary cuts through. And here we've cut through three members. Essentially what this does, by making it cut through a member, is it exposes the force that's inside that member. It exposes essentially the force on this part of the truss from this part. So this part of the truss is exerting some force. The uncircled part of the truss, the right side, is exerting some force on the boundary here. There's some force on that member, and we're going to expose that force here by cutting through it. So just like in working with free body diagrams, when we built our system boundary, we could eliminate whatever was outside, as long as we replaced it with the forces it supplied. That's what we did when we did our free body diagram here with the external problem. When we drew our system boundary around here, we cut through essentially the support forces, and we replaced those supports with the forces they supplied, and then solved for them. We're going to do the same thing here, and it looks looks a little nicer on the display. So let me on my notes. So let me go ahead and do that. So here's what it looks like in the notes. if I eliminate everything outside the system boundary, that whole right side of the truss is going to disappear. And all that will be left behind are forces, the forces that are exerted on the members that we cut through by the rest of the truss. So if I kind of flip back and forth here, there's the whole truss, there's my cut truss. So by cutting through, I have exposed these forces, FGH, FBG, and FBC. So let's go back to the page here and see how that works. So essentially what we're doing, let me redraw the free body diagram of the what's inside the truss, or inside the system boundary. So inside the system boundary, we have something that looks sort of like this. We've got joints A, H, and B, and then we've got these little stubs that we've kind of cut through. We've got this little piece of FGH. We've got this little piece of member BG, and we've got this little piece of member BC. That's where the system boundary cut through. Now, at each of these points where the system boundary cut through, we're exposing a force. We have to replace the piece of member GH that we're cutting away with the force that it exerts on the piece that's left behind. And we're just going to call that schematically FGH, the force carried by member GH. Down here where we cut through member BG, we had to get rid of this piece that is outside the system boundary, and we can get rid of that piece by replacing it with the force it supplies. So there's the force it supplies, and we'll call that FBG. And then down here, we cut away the right-hand side of member BC. So what's left behind feels a force that we'll call FBC. And then, of course, we still have the external forces. We still have that 1,600 pounds pushing down at H, and the 3,800 pounds pushing up at A. So there's the free body diagram of the section of the truss that we have isolated. Now, that can look fairly complex. In fact, it's a pretty complex force system. We've got three unknowns, and we've got angles involved. So there's some mess there. But with that more complex system, we're going to get more pieces of information. We're going to solve for all three of these in one step. Now, so let's set up our equations, and then we'll take a look at tension versus compression. So let's set up the equations. Sum of forces in the x direction. Well, first let's define our x direction. X is to the right, y positive is up, and counterclockwise moments are positive. If we take our sum of forces in the x direction, we've got all of FGH to the right. We've got all of FBC also to the right, so it's positive. Then we're going to catch a piece of FBG. In order to figure out what piece, I need this angle. But fortunately, from our original drawing with our geometry, we could figure out that angle pretty easily because we have a right triangle that's 9 feet tall and 12 feet wide. So by using inverse tangent, 9 over 12, inverse tangent, we have an angle there of 36.870 degrees. So that's our angle. And we'll leave that there, 36.870 degrees. And so we'll keep 5 sig figs for our internal calculations. Now we need the x direction piece, that would be the adjacent side, and adjacent goes with cosine. So we'd have FBG cosine 36.870 degrees. That's not a great looking sum. If this method's supposed to be a good bit more powerful, or at least easier to, in some cases, to use, it's not looking bright right here because we've got three unknowns in one equation. That's looking kind of ugly, but maybe the y direction and the moment equation will be a little better, and then we can use that information to solve for just one of these values up here. So we'll hold the x direction off for a little while, but we can set that equal to 0 since that's our first equation. We'll take our sum of forces in the y direction. Well, in the y direction, we've got a positive 3,800. We've got a negative 1,600. And then we've got a piece of FBG. FBC and FGH, they're not going to come into play. That piece of FBG is up, so it goes into the sum positive. It's FBG. And it's a fair bet that it's going to be sine of 36.870 degrees. Well, that's looking a little better. That only has one unknown. It's been a while since we had a y direction equation with only one unknown. So we've got something there that we can work with. Let's go ahead and do the moment equation. And in method of sections problems, picking the right pivot point is absolutely critical. If you ever get more than one unknown in your moment equation, you picked the wrong pivot point. At least in this class, I think it's a consequence of being in two dimensions that there should always be some pivot point that will have only one unknown. But I haven't proven that, but it may be a consequence of that. So there shouldn't ever be more than one unknown in your moment equation. The instinct you'd probably have at this point would be to pick point A. But point A is not a great point for our as our pivot point. If we picked point A as our pivot point, we'd definitely knock out that 3,800 pound force. But we'd have a moment due to the 1,600 pounds. We wouldn't have a moment due to FBC since its line of action goes through A, but we would have a moment from FBG, which is going to be weird because that's at an angle. So I'd have to do sine or cosine and try to figure things out that way. And FGH, that's going to have a moment too. So I'm going to have two unknowns as my moment in my moment equation. And that's not good. Well, generally it's going to be safest to pick one of the points you got. It doesn't make much sense to go pick some arbitrary point off to the side. So your choices in this problem are either A, H, or B. Well, if we pick H as our pivot point, we'll knock out the 1,600 pound force and FGH, but we'll have a moment due to FBC. We'll have a kind of ugly moment due to member FBG, and we'll have a moment due to that 3,800 pounds. Again, two unknowns in the moment equation. Generally, the intersection point of the most number of unknowns is where you want to pick your pivot point. Point B is the optimum pivot point here. Because if we pick our pivot point at point B, we knock out FBG and FBC. So both of those are gone. So we eliminate that ugly complex moment that we were looking at with BG. We knock out 1,600 pounds, and we're left with just two terms, FGH in the moment due to that, and 3,800 pounds. That's about the best we could hope for. So let's do our moments about joint B. So we'll take our sum of moments about B. So no moment from those two or that one. FGH, that's 9 feet away. So we've got 9 FGH. Be careful with your directions here because we're pivoting on a point that's not the typical ones that you've used in the past. So really work it out. Pinning at B, pulling to the right at H, that'll give us a clockwise moment, so negative. We've got 3,800 pounds. That'd be 12 feet away. So we have 12 times 3,800. That's 45,600. If we're pinned at B and pushing up at A, that's again a clockwise moment, so negative. All right, so things weren't looking so good with our x direction equation, but they brightened substantially with our y and our moment equations. Both of those we can solve in essentially a couple steps. One unknown, no big deal. And once we've got FGH and FBG, we can plug that back in, and that'll give us FBC. Now I'm going to put off the solution here for just a second while we go and take a look at tension or compression. Now, the biggest thing to realize here with method of sections is that we're not looking at the same thing that we were looking at with method of joints. With method of joints, we were looking at the forces on the joints due to the members. Here, we're really looking at the forces on the members. We cut through the middle of a member and we asked how much force is pulling on what's left to keep this part in equilibrium. That's the real force on the member. So fortunately, tension and compression are much easier to work with. There's not as much analysis and trying to figure out, is this tension or is this compression, and trying to explain it to yourself and make sure that you've got the right thing. And in fact, we even take that a step further in most problems. Notice how I drew these unknown forces. I drew them as pulling on the remaining parts of each of the members. Essentially, that means I've assumed tension. I have assumed the rest of the truss is pulling on each of these three members. If you make that assumption, then that means if your assumption's right, the truss is in tension, or at least that member is in tension. If your assumption was wrong, you'll get a negative answer. So in method of sections problems, as long as you always draw the forces, the unknown forces, as pulling on whatever is remaining, whatever you cut, whether that's to the right or the left. If you close to the other side, you'd get forces to the left instead of the right. But the tradition is to assume tension. It's just easier to draw. It's less awkward than drawing an arrowhead pushing in on something. So we assume tension. If our answers come out positive, that means we've got tension. If the answer comes out negative, it means compression. So interpretation of tension and compression is much, much simpler in method of sections because we essentially build it into our assumption. We assume everything's tension. And when our answers come out positive, remember, positive answers mean our assumptions were correct. When we get a positive answer, we have tension. If we get a negative answer, that really means that the rest of the truss pushes on the member instead of pulling on it. So that puts it into compression. So let's see what we've got here. So let's solve our moment equation. That looks like the easiest one to solve here. And be careful with your signs. Don't get lost in the signs. Work it out step by step if you have to. Add 45,600 to both sides. We get minus 9 FGH equals a positive 45,600. Divide both sides by negative 9. And we get a negative 5,066.7. And that's pounds. So what's that telling us? If we look at the top, we had assumed tension in member GH, but the math tells us that assumption was wrong. If I wanted to be fully correct about it, I should have drawn FGH pushing in. It's telling us that member GH is not in tension, member GH is in compression. Positive answers mean tension, negative answers mean compression. So member GH is in compression. So if we go and build up our little table up here with the members are load, this time in pounds, and whether we've got tension or compression. Member GH, we can fill in. We've got 5,066.7 pounds of force in, whoops, not in tension, in compression. Negative answer means compression. That's probably the biggest thing to keep straight between method of joints and method of sections, how you figure out tension versus compression. In method of joints, we had to look at the direction and figure it out versus the where the member was and whether it was pushing on the joint or pulling on the joint and interpret that. It's much simpler to interpret in method of sections, which is why it's a lot of people's favorite method. Tension and compression is a lot easier to deal with. But we can't go and change things just yet. We can certainly write things out in a table, but we can't say, all right, I'm just going to go flip this arrow, because we built these equations, all of them, based on the assumptions that we have here. And if we go changing our assumptions in the middle of the problem, we're going to have sign errors because our equations will no longer reflect the assumptions that we had at the beginning. So we work the problem through with the assumptions we start with. That means wherever I see FGH, I'm going to have to plug in a negative 5,066.7 pounds. So when I go and use that in the x direction equation, I got to make sure to use the negative in there. Let's take a look at the y direction equation. If we simplify the y direction equation down a little bit, we've got 2,200 pounds plus FBG sine of 36.870 degrees equals 0. I'd subtract the 2,200 pounds from both sides and get FBG sine of 36.870 degrees equals negative 2,200. And then I divide both sides by that sign. So going over to the calculator, 2,200 negative divided by the sine of 36.870 degrees. That gives us negative 3,666.7. So FBG comes out to be negative 3,666.7 pounds. So again, a negative answer. That means that the rest of the truss is not pulling on member BG, it's pushing on member BG, putting it into compression. So member BG carries a load of 3,666.7 pounds, also in compression. Now in our last step here, we have to work with that x direction equation. And we're stuck with the numerical values, positive or negative, of those symbols. So we've got to use FBG as it sits. We have to use FGH as it sits. So here FGH I'm going to replace with negative 5,666.7. So negative 5,066.7. FBC I don't know. And then I've got minus 3,666.7 times the cosine of 36.870 degrees. So we can work out some numbers here. If we take 3,666.7 times the cosine of 36.870, we get negative 2,933.4 FBC, there we go. minus 5,066.7. So combining the numbers together and adding them to the other side, we've got 5,066.7 and 2933.4. That gives us FBC carrying 8,000.1 pounds. Now that one came out positive. So that means member BC is really pulled on by the rest of the truss. Remember that these forces represent what the rest of the truss that we threw away is applying to the part of the truss we're keeping. And in this case, FBC came out positive, meaning that member BC is pulled on just like we drew it. Being pulled on means tension. So we have 8,000.1 pounds in tension. So there's the table before rounding anyway. Member GH and BG are in compression, and member BC is in tension. Let's look at that on the free body diagram here for a moment. Generally, when you've got a structure like this, and you've got gravitational loads, you've got forces pulling down, weights, generally the structure is going to want to bend kind of like this. It's going to want to bend down that way and bend down that way. Becomes kind of a U shape. It sags in the middle. Well, think about what you know from sheet metal. When you bend a piece of sheet metal to make it look sort of like that, bending upward on the ends here, you're putting the top into compression and the bottom's getting stretched out. That's in tension. So whether it's a piece of sheet metal or a bridge, it still experiences under that kind of bending load. It experiences tension on the bottom and compression on top. An airplane wing is exactly the same. When you lift up on an airplane wing, you're bending it upward essentially. The top goes into compression, the bottom goes into tension. The cross pieces can be a little harder to figure out. The cross pieces depend a little bit more on load and of course which direction they're going in. So they can be kind of a toss-up in terms of figuring out whether they're in tension or compression. But a good sanity check on your answers, at least your interpretation of tension and compression, can be to look at the bending of the structure. The bottom should generally be in tension, and the top should be in compression. So as far as rounding goes here, to round our answers off, we said 3 sig figs. So we'd have for GH, we'd have 5,070 pounds. Remember that trailing zero doesn't count unless there's a decimal point there. For BG, we'd replace that with 3,670 pounds. And for BC, we'd have to be a little more careful. If we just said 8,000, that would be only 1 sig fig. If we said 8,000 with a decimal point, that would be 4 sig figs. About the only choice you really have here is to write this in scientific notation and say it's 8.00 times 10 to the third pounds. That way we've definitely got the 8,000 value, but we've got 3 sig figs. So be careful of that when that comes up. If you get something that you can't write in the normal notation to the correct number of sig figs or whatever number of sig figs has been specified, you have to go to scientific notation. Scientific notation can always sort it out for you. So that's method of sections. So method of sections, big points. Still have to solve the external problem. Still have to figure out the reactions at the supports. The advantage to a method of sections problem is that when you only need some of the members, then you have the ability to just get some of those. You can jump right into the middle of the truss and solve one set of equations in 3 unknowns. interpretation of tension and compression is a lot easier. We assume tension when drawing our free body diagram. If the answers come out positive, then we have tension. If they come out negative, then we have compression. Any questions so far?
Nope.
All right, so let's go back to the notes here. So that's one example. Here's another example we'll take a look at, and we'll kind of start that into a little bit more of a sort of a practicum kind of session here, because that's all the new content we have tonight. On this one, let me see here. This one should have a pinned support at A and a roller support at E. So this should have a pinned support at A and a roller support at E. It's got lots of members here. We're only really interested in what's going on in member CG, CD, and GH. So those are the three members we're after. So first thing to do is first I'm going to copy it down so I've got the right information here. And I don't know why the supports aren't showing up in there, but I want to make sure we've got that. We got 4 bays at 4 meters each. Let's try that again. There we go. We've got upward cross members. Now this would be a real pain to solve, even with all the 90-degree angles. It'd be a real pain to solve by method of joints to try to figure those out. So method of sections will be really useful here. So we have our 4 bays at 4 meters each. The whole thing is 3 meters tall. We've got 45 kilonewtons. Got 60 kilonewtons. We've got 30 kilonewtons. And just for fun, a 5 kilonewton force. And that should do it. So let's take a look at that on the page. There we are. So there we've got our truss. We've got joints A, B, C, D, E, F, G, H, I, and J. So that's the truss, and we want to know what's going on in members GH, CG, and CD. So first, let's take a few minutes and figure out the reaction forces at the supports, and I'll pause here so those of us on live can work that out. And once we've got it, we'll draw through it, and then we'll work the method of sections as an example. So let's see here. All right, so in the interest of saving time here and getting right to the new content, there are the answers for the reaction forces. Common errors here, if you're having difficulty getting these numbers, biggest error is forgetting the 5 kilonewtons in your moment equation. That 5 kilonewtons is 3 meters above A. So if you picked A as your pivot point, you can't forget that 5 kilonewtons. You may have the 45 at 4, the 60 at 8, the 30 at 12. But if you forgot that, these are going to be a little bit off. So be careful, and don't forget about the X direction reaction. And if you're still having difficulty getting these, take a picture of your work, send it to me, and I'll try and help you out. All right, so let's do our method of sections. Now, method of sections, we need to find our cutting plane. We have to pick a cutting plane to use, and that cutting plane it needs to only cut through three unknown members. And in these early problems that we're working on, it's usually set up so you can just draw one cutting plane, get the problem done one setup. But in a little bit more advanced problems, and ones we'll probably work with on Wednesday night, um, we're going to want something you can't draw one cutting plane through and get everything. For example, in this problem, if I changed it slightly and said, I don't want member CD, I want member CH. Now there's no single cutting plane I can draw through that's going to get me everything I want in one step. And when that happens, we have a couple different things we can do. We either do another setup with a different cutting plane that cuts through what we want and deal with the fact that we're going to get some extra information that we don't really care about, or we can jump into method of joints. Once we know what's going on in these three members, we could do method of joints at C, and we'd get our other two members. So having the ability to flip back and forth between method of joints and method of sections can be really useful. So don't get too comfortable, I suppose, with the fact that you're always going to be able to find a cutting plane, because you may not always be able to find a cutting plane that gets you everything you want in these problems in one step. But for our examples, that's what I've set up here. So we want these three members. So our cutting plane is going to go down through here. The only question is, which side do we want to close to? We want to close our system boundary to the right or to the left. And I usually make my choice based on what is going to result in simpler equations, dealing with fewer unknowns or fewer external forces, fewer terms in my equation, all of that. And so you could close to the left. If you close to the left, you're going to end up with something that looks sort of like that as your free body diagram, which means you're going to end up with the 60 kilonewton force. You're going to have 45 kilonewtons. You're going to have a couple forces down here from A, and you're going to have your three unknowns. But if you close to the right, well, we end up with the 30 kilonewton and the 5 kilonewton force, and then one other force from E. That's one less force to deal with. We had four forces we deal with over here, only three forces here. So I think in this example, even though it's counter to what I've drawn in the notes, um, and as you practice on this, you could go and work it out as it's drawn in the notes and see if you get the same answer. You should. The answer cannot depend on the method we use to solve the equations, or that we use to set up the equations. Equilibrium is equilibrium. There's one force in this member. It doesn't matter how you find it. If you get the right one, it's only one. Can't depend on what method you pick. You're not going to get a different answer for method of joints, method of sections, closing to the left, closing to the right. So I'm going to close to the right on this one as an example of how to do that. So that'll be my system boundary here. So I'll draw my piece of the truss. And I always like to start my sketches of the piece of the truss with the members that are wholly enclosed in that boundary. So I've got one bay completely enclosed like that. And then I've got the little stubs that I've cut through. I've got one there, I've got one here, and I've got one there. So right there is where my cutting plane went through. And by default, we always draw our unknown forces, the forces we expose by cutting through these members, draw them so they're pulling on the piece of the member you're keeping. So I'm going to draw this over there like that. That'll be the force exerted on member GH. This one will be the force exerted on the member CG. And this one will be the force exerted on member CD. Then don't forget your external forces. You've got that 30 kilonewtons at G, You've got 5 kilonewtons at F, and then we have REY 62.813 kilonewtons. So there's our free body diagram of the section of the truss inside that system boundary. Always worth a check to just make sure you've caught everything. Compare your picture to where you've drawn your section, make sure you've got everything cut through and that the external forces are there. Moment of extra care there can save you a lot of time and pain later on. So let's draw our coordinate system and get our equations of equilibrium. So we need our sum of forces in the x direction. And usually in these problems, the x direction force is the x direction equation is kind of the painful one, but it's usually the last one we deal with. We've got negative FGH. We've got negative FCD. We've got a piece of FCG. We're going to have to figure out that angle. We'd have this, and we'd have the 5 kilonewtons also to the left. So let's get our angle here, and we can do that up here. We want this angle right there, so we can use this right triangle. 3 meters there and 4 meters here. So we'd use inverse tangent of 3 over 4. And that's 36.870. That number comes up a good bit with these, but 36.870 degrees. So that'd be our angle here, 36.870 degrees. We want the adjacent piece, the horizontal piece, and that's pulling to the left. So it'd be negative FCG cosine adjacent side, 36.870 degrees. And then don't forget that 5 kilonewtons. So that's our x direction sum. Our y direction sum, usually simpler since we only have one member here that's got a y component. That's an unknown. We've got a positive 62.813 kilonewtons pushing up. We've got a negative 30 kilonewtons down. And then we've got a piece of FCG down, and that'd be the opposite side, vertical side, that'd be the sine, 36.870 degrees. So that's our y direction equation. And then we've got our moment equation. Well, to set up the moment equation, we need a pivot point. And your instinct may be to go for E, the support, because that's what we've always done. But that in method of sections problems, that's not the biggest benefit. The biggest benefit is going to be at the intersection of the lines of action of the most unknowns. So if I picked joint D over here, I'd knock out FCD and the 30 kilonewton force, but I'd still have two unknowns that have moments. Joint G up here looks like a good place to go because that's going to knock out FGH and FCG. It's also going to knock out that the 30 kilonewton force and the 5 kilonewton force, since both of them have lines of action that go through G. All I'm going to have left is FCD and the 62.813 kilonewton force. I'll have to be careful with the arms, but those will be the only two forces, two terms in the moment equation. So that's nice and simple. So we'll pick the moment about point G. So let's look at the 62.813 first. We've got 62.813 times its arm. Our pivot point's right here, the line of actions like that. That's one bay away, and each bay is 4 meters. So our arm there is 4. And then we've got FCD. Oh, let's do the sign here first. If we're pivoting at G, pushing up at E, that's a counterclockwise moment. Counterclockwise moments are positive. So we've got a positive 62.813 times 4 feet or 4 meters. We got FCD, its line of action's down here at the bottom. So we need this distance here, the distance between the top and bottom of the truss. That's 3 meters. So the arm for FCD is 3. The pivot point is at G. If we pull at D, that would be a clockwise moment, and clockwise moments are negative. So there we've got our 3 equations, and we're going to fill in our table. And we want member CD. We want member CG. And we want member GH. So let's go ahead and figure out member CD. That one, the algebra is not too bad on that. We got 62.813 times 4. That's 251.25. So we have, if we bring the 3 FCD over to the other side, we've got 3 FCD equals 251.25. Divide both sides by 3. And we've got 83.751. So FCD is 83.751. And don't forget the units that are involved here. They're not pounds. Don't make the same mistake I did there. They're kilonewtons. So 83.751 kilonewtons for member CD. Now, if we were to round that to 3 sig figs, that would be 83.8 kilonewtons. Now we've got to decide tension or compression. Remember, in method of sections problems, we assume tension. We assume the part of the truss we're throwing away pulls on every member we're cutting through. It's not going to be true most of the time, but it's a good uniform place to start. That way, if we get a positive answer, we know we've got tension. And here, this is a positive answer. So we've got tension. And that makes sense physically from this being at the bottom of the truss. Usually those bottom parts of the truss are in tension. So 83.751 kilonewtons, we'll use that in our calculations, but we've got our final rounded off answer up there in the table. Let's go to the y direction. Y direction, we got a little more work to do to simplify it, but it's not too bad. If we subtract that 30, we get 32.813, and we move the FCG sign over to the other side. We divide both sides by the sign, 36.870 degrees. We've got 32.813 divided by the sine of 36.870. That gives us 54.688. So FCG is 54.688. And again, kilonewtons, and again, positive. So in this one, the cross member came out to be FCG, came out to be in tension. So member CG is in tension and rounded to 3 sig figs, that'd be 54.7 kilonewtons. So now that we've got those two, we can go up into the x direction equation. And remember that when we go into the x direction equation, or go into any time we're substituting for one of these unknown values, you have to substitute whatever that numerical value is, including the sign. That can get a little tricky sometimes. If one of these had come out negative, and we've got negative of that value, we'd have two negatives there. That'd be a positive. So you got to work out the signs and such carefully. Fortunately, here these came out positive, so that's not an issue. So we've got negative FGH minus FCD, that's 83.751, minus FCG, 54.688, cosine 36.870 degrees, minus that 5 kilonewtons equals 0. So if we crunch down all the numbers, we've got negative 83.751. We've got negative 54.688, cosine of 36.870. So that's negative 43.750. Negative 83.751, and then minus 5. And minus FGH. So minus the 5. It looks like, draw that out over here, negative FGH minus 132.50 equals 0. So here you got to be careful with your negatives because they're all over the place here. So if we really carefully work this out, add 132.50 to both sides, we have negative FGH equals 132.5. But that's negative FGH. If we divide through by that negative 1 or flip the signs on both sides, FGH is negative 132.5. You could have just added the negative FGH to both sides, and that would have done it. Kilonewtons. So remember GH, we have negative 132.5 kilonewtons. So that one came out negative. And in method of sections, as long as you make your assumptions in tension, negative answers mean compression. So remember, GH experiences a compressive force, and rounding off this to 3 sig figs would be 133. Make sure your loads are always positive. Use up the sign when you set tension or compression. Loads are always positive. It carries 133 in compression. You would never say it carries negative 133 in compression. So loads are always positive. Any questions on that one?
Nope.
All right. So let's see here. Now in the notes, I closed it the other way. So we get that section of the truss. And you can try it out and see that it works exactly the same way. It's even exactly the same angle down here. Everything works out the same. Just a little bit more of an extent to work over, a little bit higher moments because you're dealing with forces down here, and more terms involved. But otherwise, similar difficulty level. So some closing tips for method of sections for tension and compression. Let me go back to where I had said tension or compression. So method of joints, we had to deal with this kind of mirror image issue, this Newton's third law issue. And so there we had to exercise a great deal of care to make sure that we got the right answer for tension or compression. In method of sections, we're looking at the forces on the member directly and interpreting tension and compression is much more intuitive. If it's a pulling force, it's tension. If it's a pushing force, it's compression. And in the tips here for tension versus compression, make sure you practice on keeping those straight. How you figure out tension or compression for method of joints and how you figure it out for method of sections. You can't cross those two up. Use that picture I gave last week for what tension looks like and what compression looks like based on the end of the member. And remember, with method of sections, positive means tension, negative means compression. And then always be careful in selecting your pivot point. Don't just jump into a pivot point. Look at it and see which one's going to be best for you. If you carefully select your pivot points for method of sections problems, you can make the problem fairly easy. And for our purposes, you should never have more than one unknown. It's not to say you couldn't solve it. If you picked a different point, you might end up with simultaneous equations that you'll have to solve, but you could solve it. It just would take a lot of extra work. If we take a little bit of care ahead of time, we can save ourselves that extra effort. And that's about all the time we have for kind of demonstration problems. I'll put another problem up here for the practicum session in a little bit after our break. Next time, we're just doing more practice on method of sections. I'll do a couple of roof truss problems. We'll do another example, and then we'll have more practicum time there. All right, so we'll go ahead and take our break about 10 minutes or so and come on back and we'll do a practicum problem. All right, we are back from break and I've got our practicum problem set up. So here we've got some sort of crane structure. It's 24 feet tall and 16 feet wide. It's got a bunch of loads hanging on it, 16 kips here, 10 kips, maybe a wind load, and 24 kip load up at the top. And we need to find 3 of the members. We need to find out what's going on in members CB, BH, and HI. And the specification in this problem is to 4 sig figs. So we want to make sure our answers in the end are good to 4 sig figs. So pause the recording, figure out your answers, and I'll go through the solution. All right, so the first thing we're going to need is the reactions down here at A and J. So let's first look at our free body diagram for the structure. And the free body diagram is going to look something like this. Again, we don't care about the internal details, so I'm not going to waste time drawing them. So we've got this kind of Tetris piece shape to it. And we've got 24 kips up here. We've got 10 kips over here. We've got 16 kips down here. Then we've got our supports. We've got a pinned support at A, so we'll call that RAX and RAY. We've got a roller support there at J, so we'll call that RJY. Those are all the external forces. So we need our equations of equilibrium. So we need the sum of forces in the x direction. And in the x direction, we've got let's go ahead and draw our coordinate system. There we go. So in the x direction, we've got a positive RAX and a negative 10 kips. So that gives us a result immediately. If that's equal to 0, then RAX must be 10 kips. Came out positive, so we know our assumed direction is good there. So we've got one piece of information. We've got RAX is 10 kips to the right. Let's do our sum of forces in the y direction. In the y direction, we've got a positive RAY. We've got a positive RJY. We've got a negative 16 and a negative 24. There's not a lot we can do with that one just yet, since we have too many unknowns. So let's go to our moment equation. Sum of moments, and I'll pick the pivot point here, A. That means no moment from RAX or RAY. We will have a moment from RJY, and we will have a moment from all 3 of these other forces. There's not really a better pivot point, though. I guess if we maybe picked J, we would have knocked out RAX, RJY, and the 24 kip force. We would have had one fewer terms in our moment equation. But that would have just knocked out something we already knew, not really a different number of unknowns. So it's a toss-up as to whether you want to do that. So let's see here. We've got RJY, that's 8 feet away. So we've got 8 RJY. Pinned at A, pushing up at J, that would be counterclockwise, so positive. We've got 24, also 8 feet away. The line of action shoots right through where J is, so that's 8 feet away. So we've got 8 times 24. So we've got 192 there. Pinned at A, pushing down at E, that would be a clockwise moment, so negative. We've got this 10 kip force. That 10 kip force, its line of action, the closest its line of action ever gets to A is the full 24 feet away. So we've got 24 feet times 10 kips, that's 240 foot kips. Pinned at A, pushing to the left, we've got a counterclockwise moment, so that's positive. And then we've got our 16 kip force. The 16 kip force is 16 feet away, 8 plus 8. So we've got 16 times 16, we've got 256. Pinned at A, pulling down at G, clockwise moment, so negative. And that equals 0. So if we work out the numbers here, we've got a negative 192, we've got a 240, and we've got a negative 256. That gives us a net negative 208. So we have 8 RJY minus 208 equals 0. If we add 208 to both sides and divide by 8, we get RJY is 26 kips. And that's up. So we've got another piece of information here. RJY is 26 kips up. Well, now we can go back to our y direction equation and plug in what we know. We know RJY is a positive 26. So we've got 26 minus 16 minus 24. That gives us a negative 14. We add that 14 to both sides, and it looks like RAY is a positive 14 kips. So RAY, positive 14 kips. And that one was a little bit harder to try to guess because you've got the 16 kips. If just that 16 kips was there, RAY would have to be pulling down to balance this out. But we've got this 10 kips pushing to the side that's helping out. And it looks like that's more effective because it's got a 24-foot arm instead of just an 8-foot arm. It's beating the 16 kip force here. So it's putting some load on A, some compressive load on A, which is causing the reaction at the support to push up on the structure. So there are reactions. We've got step 1 done. To go further, we have to look at our cutting plane. And if we go back to what we want out of the problem, we want CB, it's that one right there. We want BH, which is that one there. And we want HI, which is right there. So right in a line, and we can close that relatively easily. So I'm going to draw my cutting plane right through there. I'm cutting through no more than 3 unknowns. And then I can close it. I think closing down here is going to be the simplest way to go. So if I close up, I'm not going to be dealing with my reactions, but I'll have all these external forces and a bigger structure to deal with. So that's what my section is going to be. So let's redraw the section, and then we'll add in the information that we know from our external problem. All right, so let's draw the section first. And like I said during the lecture, I like to draw first the members that are completely enclosed in the section. So that would be members BI, IJ, AI. I've got my reactions over here, and I know I've got 10 kips there, and I've got 14 kips here. And I had 26 kips there. And then I've got these members that I've cut through. So I sliced through member BC right there. I've got a piece of member BH right there. So I've got these cut ends. And I've got a piece of HI right there. Well, where we cut through, that's where we expose our forces. And keeping with tradition, I will draw those forces as pulling on the pieces of the member left behind. That will assume tension. So this will be member FHI. That'll be force FHI. This will be FBH. And this will be FBC. Now to finish this off, we're going to need an angle. Fortunately, though, we can get that from the geometry pretty easily. We've got a right triangle here with an 8-foot base and an 8-foot height. When the base and the height are the same, the tangent's 1, opposite over adjacent, inverse tangent to 1 is 45 degrees. So no real calculation work that we had to do there. So there's our section. So let's get our equations of equilibrium. We first got our coordinate system, x, y, and moment. Let's take our sum of forces in the x direction. So sum of forces in the x direction, we have nothing from member BC, nothing from HI because those are both Y. We've got a positive 10 kips. And then we're going to have a piece of FBH. It'll be the vertical piece, the opposite side. Opposite goes with sine. Not that it really matters to go through that argument with 45, since sine and cosine of 45 are the same, but it's not always 45. So you should keep straight which is opposite, which is adjacent. And that goes up. So we've got FBH sine of 45 degrees, and that's up. Well, that one we'll be able to solve right away since we've got only one unknown. Our y direction equation is going to be the problem on this one. Sum of forces in the y direction, we've got a positive 14 kips and a positive 26 kips. And then we've got all of FBC pulling up. And whoops, I did make an error here. Let's go back to this. That should be cosine. I got flipped around in the rotating the problem. So here we want the x direction. That's the adjacent side. Adjacent goes with cosine. So thank you to those who I'm sure are shouting out, hey, that should be cosine, not sine. I heard you, even though it was pre-recorded. So FBC plus the vertical piece of FBH, that'd be sine. So FBH sine of 45 degrees plus all of FHI. So a lot of terms there. Let's make sure we got them all. 1, 2, 3, 4, and 5, all pointing up, so all positive, and definitely the sine for the 45-degree angle. Now we need our pivot point. We need our moment. And hopefully by now you're able to see exactly which pivot point to use in this case. The best place to go would be right here at joint B. Joint B will knock out members BC and BH. FHI will be the only unknown. We will pick up this 26 kips and the 10 kips. Don't forget that one. That's a common mistake, common place to leave out. We won't have the 14 kips because that shoots right through the pivot point, but we will have FHI, we will have the 26, and we will have the 10. Nothing from those two if we pick B. So B looks like the best choice there. So sum of moments about B. Well, we've got FHI 8 feet away, so 8 FHI. If we pin at B and push up or pull up at H, we'd have a counterclockwise moment, so that's positive. The 26 is also 8 feet away, so we've got 8 times 26, 208. Pinned at A or pinned at B, pushing up counterclockwise, so positive. Then we've got this 10 kip force, also 8 feet away from the pivot point, 8 feet. So that's 80. Pinned at A, pushing to the right, or pinned at B, pushing to the right at A, that's also counterclockwise, so that comes out positive too. No other moments, so our sum of moments is 0. So we've got 8 FHI equals negative 288. Just skipping ahead on the algebra a little bit. And if we divide that by 8, we get FHI is negative 36 kips. So member HI comes up as negative 36 kips. Positive answers in method of sections mean tension. Negative answers mean compression. So member HI is in compression. But we're stuck with our assumptions for now. We'll have to keep that negative in that number. We can fix it when we draw our final answers. So negative 36 kips. We still can't do anything with Y. We're missing too many pieces. So let's go to the X direction equation. If we subtract 10 from both sides, we'll have FBH cosine 45 degrees equals negative 10. Divide both sides by the cosine of 45. And we should get 14.141. 45. Cosine divide. Yep. 142. So 14.1421. Remember, we're keeping 6 sig figs, so we have 4 good sig figs in the end. So this would be negative 14.1421 kips. Also came out negative, so that means member BH is also in compression. Now that we've got those, we can go ahead and plug into our Y direction equation. We've got 14 plus 26 plus FBC, which we don't know yet, plus FBH, which is negative 14.1421 times the sine of 45 degrees, plus FHI, which is negative 36. We got to be careful with the signs here. So we've got 14.1421 times the sine of 45. That's equal to 9.99997. So we have 14 plus 26 is 40 plus FBC minus 9.99997 to 6 sig figs minus 36. That equals 0. So we've got almost negative 46 here. We've got positive 40. So we should expect something around negative 6. Go to the calculator just to make sure we're not going to mess anything up here. And negative 36. We'll get the round off error taken care of here. So to 6 sig figs, we have FBC minus 5.99997. So member BC, we've got a positive 5.99997. So that's our final piece here. FBC is a positive 5.99997 kips. Now that one came out positive, so that means member BC really is in tension. So let's go translate these over to a table, and we'll round off our answers to our 4 sig figs. So we have our members. We had BH, CB, which really should be BC, I suppose. Let's draw that on a different one. Sometimes I miss the whiteboard. All right, so we had 3 members. There we go. We had BC, BH, and HI. The loads were in kilonewton, or were in kips. And we have tension or compression. So let's fill in what we know. We had member HI, we got negative 36 kips. So that's 36.00, though that was an exact number. There were no round off issues with that number, but to meet the objective of the problem, we'd have to put 36.00 there. And that came out negative. Negative means compression. So that says member HI is in compression. And can you kind of see how member HI would have to be in compression? You've got a bunch of load pushing straight down on this. So that's going to load this whole column up quite a bit. Then you've got this 16 kips pulling down. That's kind of levering around a little bit on A, trying to pull this whole structure down. So that's helping to put HI into compression. It's going against compression. It's trying to put HI into tension by pushing with this 10 kips to the left. The levering the other direction is trying to put HI into tension, but it's not enough. So compression wins. Member BH, we got negative 14.1421. So that's 14.14 to 4 sig figs. Came out negative. Negative means compression. So member BH, it's a cross member, so it's a little harder to see exactly how it's in compression. But I'd look at it as, well, this column here this is being pushed down. H is going to be pushed down a bit, and as H gets pushed down, this is going to be put off to the side. It's going to be try to make the length of BH shorter, and since the B can't really move to the side, it's restrained by BI. That's going to put BH into compression. Same with pulling on G here. As you pull on G, that's really pushing HI into compression, which is helping to put BH into compression. And then remember BC. BC, we had 5.99997 to 4 sig figs. That's a nice clean 6.000. And that came out positive, so that's tension. And there we can see the tension with BC, primarily because of this pulling down with the 16 kips. Pulling down with that 16 kips is trying to tip the whole top of this structure clockwise. So it's stretching out member BC. So BC is in tension, but not by much, because this 10 kips force is acting against it. that 10 kips force is trying to rotate everything back. And the combination between this compression in BH and the lowered tension in BC is why there was a pushing up force required at the support at A. So there we go. There's our answer for our table anyway, for our practicum problem. So don't get thrown when the problem looks really complex. This would be a pretty nasty one to have to work out by method of joints, although I guess not so bad because you could start at A and J, or start at J, then work A. You maybe get I and B, and you get it in a few steps, but could be a good bit more work. So method of joints, long series of small sets of equations. Method of sections, shorter series of more complex equations. So you get more information per step. You don't have to take as many steps. All right, that is it for tonight. Next time we'll do more practice problems. Have a good night. I will see you Wednesday evening.